Section 2.3 in our book here is entitled Proving Theorems, and what we're going to be going through here is how we go from knowledge that we already have about geometry and algebra and kind of using it to find new information. So if we recall the definition of midpoint, we said that a midpoint, that if M is a midpoint between A and B, then AM equals MB, meaning if we look at the picture here, M is the midpoint between in segment AB, that AM is the same length as MB, so midpoint's in the exact middle. Now we're going to use that to prove the midpoint theorem, which actually has the same start. It says if M is the midpoint between A and B, oop, I don't know what I was writing there. Our conclusion is that AM equals 1/2 AB. We would also conclude that MB equals 1/2 of AB. So basically we're saying that instead of saying that this piece is equal to this piece, we're saying that AM, that piece, is 1/2 of this whole thing, and MB is 1/2 of the whole thing. It seems kind of logical, and most people would have figured that out on their own. But this is, again, one of the things that we do in geometry. We start out with our easier ideas. We're actually going to go through a proof going from what we already know to this statement right here, that AM is 1/2 of AB and so is MB. Okay, now we know we have the given M is the midpoint of AB, right? So anytime we do a proof, we most often start with our given. Sometimes the given's not the first step, but it's oftentimes a good start. And when we do a two-column proof, we say M is the midpoint of AB, and then over in the reasons we say the reason we know that, it was given to us right here. So our reason is given if it's something that was given right at the beginning. Now my next statement is that AM is congruent to MB, or AM equals MB. All right, and that's the definition of midpoint. Next, I'm going to say that AM plus MB equals AB. Now this comes from the picture here. We're saying that AM plus MB equals AB. And you might recall that anytime we have a point between two, it doesn't have to be a midpoint all the time, but we know that the two smaller segments add up to the larger segment. So this is actually segment addition. Next, I say AM plus AM equals AB. What I did here was I took this statement and I took out this MB and I replaced it with an AM. Now why am I allowed to do that? Because right here I just said that AM and MB were the same. So if two things are the same, I can replace one with the other. What says that I'm allowed to take something and replace it with something it's equal to? Well, that's a simple substitution. Okay, that's our substitution. Now I actually simplified here. Sometimes some books will put this as a separate step. They'll take AM plus AM equals AB and then do another step that says 2AM equals AB. This would be a simplification step because AM plus AM is 2AM. But I put that in the same step here. From here, from 2AM equals AB, I said that AM equals 1/2 AB. Well, what did I do from this step to this step? I had 2 AMs, now I only have 1, and then this side is half the size it was before. So what I actually did here was I divided by 2 on both sides. And to divide AB by 2, you get 1/2 of AB. So the strategy, or the reason I can go from here to here, is because I'm allowed to use division property of equality. Because I just took an equation divided by 2 on both sides. So that's the first part of what I was trying to prove. AM equals 1/2 AB. So I've got that part done. Let me just connect that. Now I also wanted to prove that MB is half of AB, so I'm just going to take this and I go right down to here. Now I took AM and replaced it with MB because again, AM is equal to MB. So I'm allowed to do that because of substitution. And now we've just proven the midpoint theorem. The angle bisector theorem is a lot like the midpoint theorem in that we have a definition of angle bisector, which if you look in your notes, it says if we have a ray BX bisecting angle ABC, that angle ABX right here and angle XBC right here are congruent. Now I'm going to number these angle 1 and angle 2 just to make my proof a little bit simpler here when you're looking at this, so it's a little quicker for me to go through here. So I'm going to do a 2-column proof with statements and reasons, and I'm going to say what I'm going to try and prove with the angle bisector theorem is that if ray BX is the bisector, then angle ABX, angle 1, is half of angle ABC, and so is angle XBC. Angle 2 is half of ABC. So the angle bisector theorem has the same start as the definition of angle bisector. It says if ray BX bisects angle ABC, then angle ABC, well, the measure of angle ABC, is equal to 1/2. Oh, sorry. The measure of angle ABX equals 1/2 the measure of angle ABC. That's our angle bisector theorem. So we're going to prove it right here. So step 1, we say, well, let's take a look at what we're given. BX is the bisector of ABC. I'm just going to go ahead and write that down. I'm going to say ray BX bisects angle ABC. Why am I allowed to say that in here? Well, it was given. Anytime it's given, you can just write, oh, that was given to me. Easy peasy, 1, 2, 3, Step 2, I'm going to go ahead and say that angle 1 and angle 2 are congruent using this picture up here. See, it's a little bit quicker to write angle 1 and angle 2 on here than write angle ABX and XBC, but that's going to end up being the same thing. Okay, so when we're doing our proof here, I'm going to say, instead of ABX, I'm going to write angle 1, and XBC, I'm going to say angle 2. Now, the reason I'm allowed to say that those two are equal is because of the definition of an angle bisector. Definition of angle bisector. For step 3, I'm actually going to use my angle addition postulate. Remember in the last proof we used segment addition. I'm going to use angle addition here and say angle 1 plus angle 2 equals angle ABC. Now technically I should say the measure of angle and the measure of angle. So I should have these little m's here. And the reason I'm allowed to say this is because an angle plus another angle, when they're two adjacent angles like this, equals the larger one. That's our angle addition postulate. Next, I'm going to go ahead and say that angle 1 plus angle 1 equals angle ABC. I'm not going to put those little m's in here because the slate I'm writing on, my m's come out to just be little squiggles, but I just took angle 2 and I replaced it with an angle 1. And I'm allowed to do that because of substitution. And I'm actually going to make this a separate step this time, and I'm going to say 2 times the measure of angle 1 equals the measure of angle ABC. And the reason I can say that, I'm just simplifying. Angle 1 plus angle 1 is 2 angle 1s. And from here, I'm just going to divide by 2 on both sides and say, well, now the measure of angle 1 equals the measure of angle ABC, 1/2. Ugh. 1/2 the angle ABC. and that's what we were trying to prove. And I got there from this step to this step by saying division property of equality. Okay. When completing a proof, it's important to keep your eye on what it is you're trying to prove. For example, when I was here, I said, oh, I have two measures of angle 1. I just wanted 1 for my proof statement. You want to end up with this statement. So basically with a proof, you're given a starting point and an ending point, and you just got to show how to get there. Okay. Two other things to talk about in this section are deductive reasoning and inductive reasoning. Deductive reasoning is actually what we just did. We use logical steps to come to a definite conclusion. Inductive reasoning is a little different. We use patterns for inductive reasoning. Inductive reasoning often uses experience. For example, if your friend came and picked you up every day in a truck. Yeah, I know, that's a beautiful truck. Monday, he came and picked you up with a truck. Tuesday, Wednesday, Thursday, Friday. Every day of the week, your friend came and picked you up in a truck. Well, come the following week, you would expect your friend to show up in that truck again. But what if he doesn't come in a truck? What if he shows up in a Wienermobile? You know, a Wienermobile's got a bun in there. I know, I'm an artist. It could happen. So inductive reasoning, we're kind of using uh, what we expect to happen. Deductive reasoning is what we're going to use a lot in geometry. Inductive reasoning, patterns, experience. Um, you could use inductive reasoning when solving pattern problems with numbers. If I started writing numbers down on this piece of paper, and you were saying, oh, I'll bet you your next number is going to be 21. Well, judging by this pattern, it is, because I was adding 3 each time. That's deductive and inductive reasoning.